All right, welcome everyone. In this lesson, we're going to introduce the idea of infinite limits. So specifically, we're going to see how to find the infinite limits of a function using graphical, numerical, so if we had like a table of function values, or algebraic means. And related to this idea of infinite limits is the idea of vertical asymptotes. So we're actually going to see what these are and how to find these as well using our infinite limits. All right, so let's get started. We're going to start with the graphical approach here. And here we have a function, g of x, the graph of this function. And we see something interesting happening around x equals 2. We see that the graph here is getting large positive on either side. The height of our curve here is getting large positive on either side. So specifically, on the left side, let's start with the left side here. And we see that the interesting behavior is kind of centered around x equals 2. So on the left side, what's happening? As these input values of our function get closer and closer to 2, what's happening actually to the height of our curve? Well, the height of our curve is getting really big. It's going up and up and up. The same thing is happening on the right side. So if we look on the right side, what's happening as these input values get closer and closer to this x equals 2 here? Well, we see that the height of our curve on that side is also getting really large positive. It's going up and up and up. So how can we indicate this behavior? What's the notation that we can use? And the notation that we're going to use involves limits, but we're going to introduce a special symbol, the infinity symbol, to help us with this. So for the left-hand limit, we say that the limit of our function g of x as x approaches 2 from the left is equal to positive infinity. And that's because the height of our curve it's going up and up and up. It's getting large positive. Same thing is happening on the right side. So the notation there is for our right side notation. The limit of our function g of x as x approaches 2 from the right, we say is equal to positive infinity as well. And again, that's because the height of our curve is getting large positive. So the graphical interpretation here is we're really looking at the height of our graph. And if it's getting large positive, well then we use this positive infinity symbol. Now if the height of our curve was getting lower and lower, was getting large negative, well then you can kind of guess what we would use. We would use minus infinity. Now something interesting is happening here in that the behavior on both the left and the right is exactly the same. It's getting large positive on both sides. So the height of our curve is getting large on both sides. So we can actually say a little bit more. We can say that our overall limit, just the general limit as x approaches 2, regardless of direction, well, that's infinite as well. And that's because it's a similar behavior on both sides, the left and the right side of this x equals 2. All right, so for a graphical interpretation here, we're really looking at the height. Now for a numerical, where we have like a table of values, what we're doing here is, well, here we have this function f of x, and we have some of the function values here. And in the x column, this is our input values. And over here, these are our output values. And so what we see here is that these input values, we have 0.9, 0.99, 0.999, and so on. These input values look like they're getting closer and closer to the number 1. So over here, these are our inputs. And it looks like x is approaching the number 1. Now all these values are slightly smaller than 1, so we can actually be a little bit more specific here. We can say x is approaching 1 from the left. And what do we see about the corresponding outputs? So as we read down this table, we see that our inputs are getting closer and closer to the number 1 from the left, slightly smaller values. What's happening with our corresponding outputs? our function values. What's happening with these outputs? Well, we see that they're getting larger and larger negative as we go down the list here. So f of x is getting large negative. And the symbol that we use for that is minus infinity. And so to interpret this behavior, to introduce a notation for this behavior, we say that the limit of f of x as x approaches 1 from the left is equal to minus infinity. And so the fact that our outputs are getting large negative, we introduce this minus infinity. So for large negative, we use the minus infinity symbol. For large positive, we use just infinity or positive infinity. All right, so this is what we might see in a numerical approach. We have our table of values here, and as we read down the list, it looks like the function values are getting larger and larger. In this case, negative. All right. So let's just formalize some of these definitions here. So we have two potential infinite limits. If we're looking at the limit of a function f of x as x approaches a, it could be positive infinity, and that's where the outputs are getting very large positive. Or if they're getting very large negative, then it's minus infinity. So just to keep track there. And, we've written these definitions, so as our input values x get closer and closer to the value a, we're seeing some kind of behavior with our output values. They're either getting large positive in the case of infinity or large negative in the case of minus infinity. But there's similar definitions here for left-hand and right-hand limits as well. So just a little note here. Similar definitions for x approaching a from the left and x approaching a from the right. So just to keep that in mind. Now just a few kind of important warnings here or notes. These are things we want to remember. So first of all, this infinity symbol, it's a symbol, it's not a number. So we can't do normal arithmetic with it. So I don't want to see things like, so just as an example, infinity minus infinity is equal to 0. No. That's not something I want to see. Or infinity divided by infinity is equal to 1. No. I don't want to see that either. So we can't do normal arithmetic with infinity. So think of it just like a symbol, where it's just a statement. It's just a notation that we're using. It's not like a number that we can do regular arithmetic with. So we just want to be careful about that. So no for both of these. I don't want to see this. We'll see how to deal with that later on. But for right now, that should be a red flag. Now, technically what's going on with these infinite limits is the limit does not exist. So that's something to keep in mind, is we're using this symbol to say that the limit of f of x is equal to infinity or minus infinity. But technically the limit does not exist in this case. But it does not exist in a very specific way. And so using these infinity symbols, it gives us a way to express the kind of the very specific way that the limit does not exist. And we've seen this, for instance, in the graph. So if we said the limit of a function does not exist, we'd have no idea of what the graph would look like. But if we say that the limit of our function is equal to infinity, well, there's a very specific picture in mind. It has to look something like this. So it kind of gives us a way to gives us a little bit more information than just saying something the limit simply does not exist. So if we can be more specific, that's what we're going to be. We're going to use infinity or minus infinity where it's applicable. Okay. So that's the definition, a little bit on the notation there as well. All right, how do we actually find these? So how do we actually locate an infinite limit? Well, it's nice because for the most part, there is a special case or two here, but infinite limits usually occur when we have division. So that's the kind of the key word here is, when we have division, as soon as we start dividing by variables, we want to make sure we're not dividing by 0. And if we do divide by 0, well then that might be a place where we have an infinite limit. So they usually occur where we have division, and in particular, they usually occur when we attempt to divide a non-zero number by 0. And so we're going to call this a C over 0 form because these are going to show up quite a bit. So we have this non-zero number up here. Can be any other number except 0. And what we're trying to do is we're trying to divide that by 0, which we normally can't do. But what's happening here then in the behavior of our function is it's getting either really large positive or negative. So being able to identify these forms is going to be very important to helping us locate an infinite limit. All right, so we're presented with a limit. We see that we have division. What are we going to do? Well, the first step is we want to identify that the limit is actually one of these C over 0 forms. So if x is approaching a number, take that number, plug it into the function, and see what you get. And if you get a non-zero number divided by 0, you're going to have an infinite limit. So that's the second step. Recognize that when you have this form, it means the limit is either going to be positive infinity or minus infinity. We just have to decide which. And the way we do that is with a test number. So we're going to use a test number to help us determine if the result is going to be positive or negative. All right, so this is our strategy here. Now there is one special case. So for the most part, we're going to see these when we have division. But there is a special case that shows up quite a bit, and that's with log functions. So the most common one we use is the natural log. And we're approaching, x is approaching 0 from the right. This is an infinite limit, and it's equal to minus infinity. And turns out this result is also works for just any of our other standard log functions as well. So not just the natural log. Natural log is the one we use the most, though. So our log functions have a infinite limit, even though there's no explicit division going on here. So this is just a special case that we need to keep in mind. All right. So related to these infinite limits is this idea of vertical asymptotes. All right, so what is the definition of a vertical asymptote? Well, it's the vertical line. Here's the equation of our vertical line, x equals a. And this is called a vertical asymptote of the curve y equals f of x, provided there is an infinite limit on either the left side, the right side, or both of the sides of a. So it could occur just on the left, it could occur, an infinite limit could just occur on the right, or it could occur on both sides. So here we have this function g of x that we saw before, this graph here. And what we saw is that there's an infinite limit on both sides of this graph. So what we're seeing here is there's a vertical asymptote at x equals 2. And what's happening here is the graph of our function is getting, as we get closer and closer to, as the inputs here get closer and closer to 2, the graph of our function is getting closer and closer to this dotted line. So that's actually our vertical asymptote here. It's this dotted line. So our graph, the graph of our function here is getting really close to that line. It's approaching that line as we kind of move further and further up here. All right, so that's just one example, but let's kind of draw a few other pictures where we have a vertical asymptote at x equals 2, just for the practice here. So we might have something maybe it gets large negative on either side. So we have our vertical asymptote here. Use red. Yep. Come on, red. Here we go. And maybe our function is getting large negative. So maybe it's doing something like this on either side of x equals 2. So here's an example where the limit of our function as x approaches 2 is equal to minus infinity. Because on both sides, the left and the right side, it's getting further and further down. But it doesn't, we don't have to have the same thing happen on both sides. So, we could cook up examples where maybe it's different on either side. So here's another one. So maybe here at x equals 2, maybe on the left it's getting large positive, but maybe on the right it's getting large negative. Maybe it's something like this. And in this case, because this behavior is different on either side, on the left side it's getting large positive, on the right side it's getting large negative, what we would say then is the overall limit in this case as x approaches 2 is equal to, well, it does not exist. But we could be a little bit more specific with our left and right side limits. We could say as x approaches 2 from the right is equal to positive infinity, or as x approaches 2 from the left is equal to minus infinity. But the overall limit here, and that's what we're talking about, as just x approaches 2, that does not exist because the behavior is different on either side. So in that case, we would actually use this DNE. But in all three of these cases here, we have a vertical asymptote at x equals 2. And it doesn't have, we don't have to have these infinite limits on both sides. It could just happen on one of the sides. So with like natural log, the special case of natural log, what does the graph of natural log look like? This is one of those graphs. It's going to be helpful to know. The graph of the natural log, and most of our log functions, looks like this. And so we see that as we get closer and closer to 0 from the right, the height of our function is getting larger and larger negative. And so that's what this limit notation is saying. As our inputs get closer to 0 from the right, the actual function values get larger and larger negative. The height of our curve gets larger and larger negative. And so this has a vertical asymptote at x equals 0. And the log function is undefined for negative x values, so there is no left side. It's only the right side here, but that's enough to say that we actually have a vertical asymptote. The graph of this function has a vertical asymptote at this line x equals 0. So it could just be we have an infinite limit on just one of the sides, or it could be on both of the sides, or it might just be, different behavior on either side. And so one little comment here about our definition. When we talk about a vertical asymptote, we're using this x equals a here. And what that is, that's the equation of a vertical line. So there's just a little note here. X equals 2 is the equation. So when we say find the vertical asymptote, we actually need the equation of the line. It's not enough to say 2. 2 is just a number. That really doesn't answer the question. We want to know what is the vertical asymptote. We actually need the equation for the line. So x equal to 2 is the actual equation here. 2 is just a number. So just keep that in mind when we're finding vertical asymptotes. We want the actual equation of the line. Alrighty. And so again, we know for the most part, we have a vertical asymptote at our x values where we attempt to divide a non-zero number by 0. So for the most part, a lot of the functions we're going to be looking at that have a vertical asymptote, there's going to be some kind of division involved. And so the way we can locate our vertical asymptotes for most of our functions is to figure out where our denominator is equal to 0. And then once we determine that, then we're going to calculate our limits. We're going to show that there is an infinite limit on either the left side, the right side, or maybe both of those sides. So we're going to set our denominator equal to 0, figure out the x value that makes our denominator 0, and then calculate the left and the right side limits as x approaches that number. Now again, there is that special case of our log functions, which has a vertical asymptote at x equals 0. And we kind of looked at that picture. And not just natural log, all of our standard log functions have a vertical asymptote at x equals 0. All right, so let's try some examples. So let's look at example 1. We're going to compute this limit, the limit of 1 plus x over 4 minus x as x approaches 4 from the left. All right, so what are we going to do? So step 1, we're going to just take this number that x is approaching and we're going to plug it into this function. So we're going to plug in x equals 4 right into the function, just to give us an idea of what's happening. All right, so let's take 4, plug it in. We get 1 plus 4 over 4 minus 4. We get 5 over 0. So what we're seeing right here with this 5 over 0, this is undefined. We can't divide 5 by 0. But this is what we're attempting to do. And this is our c over 0 form. So step 1, we just identified that this limit is our c over 0 form. So right away, it's a non-zero number. We're attempting to divide it by 0. We can't do this. So this is a special form. And what this means is that our limit, there's only two options. This limit is either positive infinity, it's getting larger positive, or it's getting very large negative. So this limit is either positive infinity or minus infinity. And we have to figure out which of these it's going to be, positive or negative. And the way we do that is with a test number. So step 3 is we're going to use a test number to figure out if the result is positive or negative. So since x is approaching 4 from the left, if we look at our limit notation here, x is approaching 4 from the left, the test number that we have to pick has to be close to 4, but slightly smaller. So we have some choices here. One choice, we could take our test number to be 3.9. It's close to the number 4, but we've subtracted a little bit. It's slightly smaller. It's on the left side of 4. So we could use this test number. And what we're going to do is we're going to plug it into this function and see if we get a positive number or a negative number. So we're just going to plug it in. All right, so what do we get when we plug it in? Well, we get 1 plus 3.9. So we're just plugging into our function right here. So 1 plus 3.9 divided by 4 minus 3.9. And what is that? Well, we get 4.9 on the top, and we get positive 0.1 on the bottom. And this result, I mean, we could use, if you really needed to, you could use a calculator to get this exactly, but we don't really care about what number this is. We care about whether it's positive or negative. And we have a positive number divided by another positive number, so the result is positive. And so we can say that we first identified that this was a c over 0 form. That told us our limit is either going to be positive infinity or minus infinity. And then we used a test number to see that our function values on the left side are positive. So this limit is going to be positive infinity. So we say that this is equal to positive infinity. All right, not too bad. Let's try the right-hand side. Let's do the limit of that same function, 1 plus x over 4 minus x, as x approaches 4 from the right. So if this was our fresh start here, the first step would be to plug in x equals 4 and just see what's going on. So we plug in the number we're approaching. We've already done this, but let's just write it out again. 1 plus 4 over 4 minus 4. It's 5 over 0. So this is telling us we have a non-zero number divided by 0. This is what this looks like we're trying to do. So this is a c over 0 form. This is a key step. We need to identify that this is what's going on. And what that tells us then is that the limit, because we have this very specific format here, the limit is either positive infinity or negative infinity. And we have to figure out which of these is it going to be. So we're going to do a test number, just like we did. And now this is where we have to kind of pay attention to how we're approaching 4. Now we're approaching 4 from the right. So what that means is we're getting closer, our input values are getting closer and closer to 4, but they're slightly bigger. The plus, just think of the pluses, it's slightly bigger. We've added a little bit more in. So a test number has to be on the right side of 4. So we might use, as our test number, 4.1. It's close to 4, but it's slightly bigger. We've added a little bit more on there. We plug it in. So plug into just the original function there. And what do we get when we do that? Well, we get 1 plus 4.1 divided by 4 minus 4.1. And if we do the arithmetic there, we get 5.1 divided by negative 0.1. And so we get a positive number divided by a negative number. And what that means, when we have a positive divided by a negative, the result is negative. So this is a negative result here. Positive divided by a negative is negative. So we went through, identified that we had the correct format here, which told us that we either had, our limit was either positive infinity or minus infinity. Then we used a test number to actually figure out, well, all of our function values are negative on the right-hand side. So there we go. We've identified that this limit is minus infinity. The function values are getting larger and larger negative. All right, so let's put it all together. We found the right-hand limit was minus infinity. We found the left-hand limit was infinity, positive infinity. And because those are different, we say that the overall limit, well, does not exist. So the limit as x approaches 4, the overall limit here, does not exist. And that's because the left and the right side are just doing very different things. So we say that that overall limit does not exist. All right. Let's try one more. But going back, the question didn't ask to do it, but what we found in part A and what we found in part B is that we do have these two infinite limits on either side. And so we could actually say this function, it's not necessary, just kind of a little bonus here, and that's this function does have a vertical asymptote at x equals 4. So there's infinite limits on either side there. Kind of a little bonus. All right, let's try one more, just for the practice here. So we're going to show that the function tan of x has a vertical asymptote at the x value pi over 2. All right. So first thing, when we think of vertical asymptote, what we, to show that a function has a vertical asymptote, what we need to do is we need to show that it has an infinite limit on at least one of the sides, the left side or the right side. So that means we need to calculate, two potential limits. We want to do the limit of tan x as x approaches pi over 2 from the left. Show that that's potentially positive infinity or minus infinity. And just for the practice, it's good just to do both the left and the right. But we only need one of them for us to actually have a vertical asymptote. But just for the practice, then we'll also do the right side limit. So x approaches pi over 2 from the right. All right. Now, tan x, when we look at it, it doesn't look like we have division there. But a lot of our trig functions, we can rewrite these in terms of sine and cosine. Those are kind of our two principal trig functions that we refer back to. And it's no different with tan x. We can rewrite tan x in terms of sine and cosine. And so another way to express the tan function is sine of x divided by cosine of x. So there actually is, it didn't look like it at first, but there actually is a quotient going on here. So we do have division. All right. So with division in mind, let's go through our steps for an infinite limit. So step 1. Let's plug in the number we're approaching. Let's plug in pi over 2. So, and let's use the sine over cosine version. So when we do that, we get sine of pi over 2 divided by cosine of pi over 2. And these are values we should know. So pi over 2 is one of our main angles that we use when we discuss the trig functions. So sine of pi over 2, that's a value we should have memorized. Same thing with cosine of pi over 2. It's just going to make our work a little bit easier. So sine of pi over 2 is 1, and cosine of pi over 2 is 0. So this is undefined. We can't divide by 0. This is undefined. But what we're showing here is that we actually do have a c over 0 form. And what that means is we know what's happening. The limit is going to be infinite. So there's only two choices here for what's going on, plus infinity or minus infinity. We just have to figure out which, positive or negative. All right, so we need to do a test number. And we're doing a test number for the left-hand limit. So x is approaching pi over 2 from the left. All right. So this is the left side. And to help with this, let's graph. Let's look at the graph of sine and cosine. So again, sine and cosine, these are trig functions that we're going to be using quite a bit. So it's going to be helpful to have their graphs memorized as well, not just these values. So sine, what does sine look like? Let me move that line up a little bit. There we go. And so sine starts at the origin, and then it looks something like this, and then it keeps repeating. And so where it hits this maximum, this peak right here, this is pi over 2. Now what about cosine? What does cosine look like? Well, cosine kind of has a very similar look as sine. It just starts at its maximum, and then it goes through a very similar sort of pattern. So cosine starts at the maximum, and then it does something like that. And then it keeps repeating on. And so at pi over 2, that's where we cross the horizontal axis here. All right. So it's helpful to have these pictures in mind. So when we're talking about a test number, when x is approaching pi over 2 from the left, if we're thinking of sine over cosine, well, let's look at what's happening on the left side of the sine curve to the left of pi over 2. So to the left of pi over 2, we're above the horizontal axis. So it's positive over here on the left. So our sine curve is positive on the left side. Now what about for our cosine function? Well, it's also above the horizontal axis, so it's also positive. The height is positive over here. So cosine is positive. So we have a positive divided by a positive. The whole thing is positive then. So we only had two choices. We identified that it was a c over 0 form. The limit is either positive infinity or minus infinity. And we showed that the function value for tan is positive because it's positive over positive. So this is going to be positive infinity for our left side limit. Now for the right side limit, it's a lot of the same work. So we're still approaching pi over 2 from the right. So we would still plug pi over 2 in, see that it's a c over 0 form. The fact that it's a c over 0 form tells us there's only two choices, positive infinity or minus infinity. So this is all going to be the same. And so the only thing that's different here is step 3. So what's going on with step 3? We want to do a test number, and we want to look at what happens on the right side. So x is approaching pi over 2 from the right. And if we go to our graphs, it helps to have these graphs kind of in mind or sketch them out. We're looking at sine over cosine. And so if we go to our sine curve and we identify pi over 2 and look to the right of that, well, it's positive. To the right of pi over 2, immediately to the right of, eventually if we go far enough, then there's function values. But if we go immediately to the right over here, they're positive function values. Now what about for cosine? So we go to our cosine graph, identify where pi over 2 is on there, and then look immediately to the right. And here we see that we dip below the horizontal axis. So the function values here are negative. So for cosine, it's negative on the right side. So when we have a positive divided by a negative, an odd number of negatives here, the result is negative. And so what that means is there's only two choices. The limit, because it's the c over 0 form, is either going to be positive infinity or minus infinity, and we just identified that our function values are negative. So on the right side, the limit of tangent is minus infinity. And showing one of these is enough to show that our function has a vertical asymptote, but it's helpful to just get into the habit of, seeing what both are doing. So on the left side, our function is getting very large positive, and on the right side, our function is getting very large negative. So this is enough to show that we have a vertical asymptote at pi over 2, at x equals pi over 2. All right, so that's going to do it for our infinite limits. In the next lecture, we're going to investigate how to just kind of calculate standard limits using algebraic means. So we'll see you then. Bye-bye.